The image came down clean. Too clean, in fact. Webb's mirror locked on Uranus, and the rings appeared sharper than anything Voyager 2 sent back in 1986. And for a moment, the room did what rooms do when something works. Then a temperature reading came through that engineers checked, and checked again, and checked a third time before releasing. It didn't match the model. Not off by a rounding error, off by a category. The public got a stunning photo. The scientists got something colder than a photo. They got a planet emitting more internal heat than a dead world should. Rings glowing at wavelengths no one predicted. An atmosphere behaving as if something invisible was stirring it inside. This wasn't a triumph at all. This was Webb quietly telling us that 40 years of certainty about the outer solar system may have been built on a single, fragile glance. Now stay with me, because the story you were told about this image is not the story the data tells. Wherever you're watching from, whatever time it is where you are, take a second and ask yourself honestly. When NASA drops a headline that says, "Stunning new view," how often do you wonder what got left out of the caption? Because here's the pattern. The image is real, the wonder is real, and the anomaly buried inside it is also real, and it did not make it into the press release the way it lives inside the science. Uranus is not supposed to be doing what Webb caught it doing. That's the thesis. The reason Webb's image shouldn't be possible is not poetry, it's a scientific admission. Our model of the outer solar system has a hole in it, and that hole doesn't stay contained to one planet. It reaches into every ice giant, every sub-Neptune, every so-called habitable exoplanet we've announced in the last decade. Uranus is the closest example we have of the most common type of planet in the galaxy. Webb just showed us we've been reading it wrong. Here's what stacks up. Voyager 2 flew past Uranus in 1986 and measured its internal heat flux as effectively zero. That single measurement became the foundation. Uranus was classified as the dead ice giant. Neptune radiates extra heat, Jupiter does, Saturn does. Uranus, we were told, did not. And every textbook got built on top of that one afternoon of data from 4 decades ago. Webb's infrared readings now suggest that classification is wrong. The signal isn't zero, it's structured. It's the signature of an active interior. And if that's true, the planet we've been calling dead has been quietly working the whole time, and we didn't have the instruments to see it. By the end of this, you'll understand why this image is being treated inside the community as a warning, not a postcard. The official version of what Webb saw is short, warm, and celebratory. First infrared view of Uranus. Rings never before captured this clearly. A triumph of the telescope. Every outlet ran that framing, and none of it is wrong. It's just incomplete. Because the same data that produced the photo also produced measurements that don't line up with anything we thought we knew. Start with the thermal profile. Voyager 2's 1986 numbers said Uranus barely radiated internal heat. Webb's infrared observations are showing thermal features that shouldn't exist on a planet that quiet. The two datasets, separated by nearly 4 decades, disagree at a level that isn't explainable by instrument drift. One of them is wrong, or the planet has changed in ways our models don't predict, or the original measurement captured a temporary state we mistook for a permanent one. Any of those 3 answers is a problem. Then the rings. Ground-based follow-ups after Voyager gave us a specific count. Webb is showing more of them, glowing at wavelengths that shouldn't produce that kind of signature from icy debris of the composition we assumed. Something in the ring chemistry doesn't match what we thought was there. And the atmosphere. Uranus has an 84-year orbit and one of the strangest axial tilts in the solar system, tipped over on its side, which means its seasons are 20-year monsters of sunlight and darkness. Our models predict a certain rhythm driven by that cycle. Webb is showing seasonal shifts running faster and more chaotically than that rhythm allows. The weather on Uranus is not behaving like the weather on the Uranus in our textbooks. Here's the reframe. This is not a story about Webb showing us Uranus. This is a story about Webb showing us that we were wrong about Uranus for 40 years. And being wrong here doesn't stop at Uranus. Every ice giant model, every sub-Neptune calculation, every extrapolation to the thousands of similarly sized worlds we've catalogued around other stars traces back to what we thought we knew about this one planet. Webb quietly dismantled a load-bearing wall of planetary science, and that's the part that isn't in the press release. Not because anyone is lying, because stunning image fits in a headline, and the foundational model of ice giants may need to be rewritten, doesn't. The wonder is easier to defend. The wonder generates public support. The anomaly generates scrutiny, and scrutiny is expensive. The public got the frame that keeps the funding stable. The scientists got the frame that keeps them awake. Both frames come from the same data, but only one of them is honest about what the data means. To understand why this anomaly is more than a curiosity, you have to understand how an ice giant is supposed to work in the first place. Ice giants form in the cold outer regions of a solar system, far from the sun, where water, methane, and ammonia can exist as ices instead of gases. Under crushing pressure, those ices form mantles thousands of kilometers deep, wrapped around rocky cores and topped with thick hydrogen and helium atmospheres. The formation process releases enormous amounts of gravitational energy, and that energy doesn't dissipate quickly. It stays trapped inside, radiating slowly outward over billions of years. Every ice giant is supposed to still be leaking that primordial heat. Neptune does it. Neptune radiates about 2.6 times more energy than it receives from the Sun. That excess is the fingerprint of an interior still working, still convecting, still bleeding out the leftover fire of its formation. Jupiter does the same at a much larger scale. Saturn does it. This is not exotic physics. This is the baseline behavior of a giant planet. Uranus, according to Voyager 2, did not. The 1986 measurement put Uranus's internal heat output at essentially nothing, barely distinguishable from zero. That single data point turned Uranus into the anomaly, the planet that had somehow lost its internal engine. Imagine a row of houses in winter. Every house is warm inside because every house has a furnace running, except one. One house sits at exactly the outside temperature, as if the furnace stopped centuries before the neighbors did. That is what Uranus looked like for 40 years. The one house on the block with no fire. The problem is that Webb is now showing infrared signatures that a dead furnace shouldn't produce. The heat signal isn't zero anymore. It's small, but it's structured, meaning it has spatial patterns. Warmer regions and cooler regions. The kind of asymmetry that only happens when something inside is actively moving heat around. A truly dead interior would radiate flat. This one doesn't. There are two ways to explain this. One is that Voyager 2 caught Uranus during a brief anomalous state. The other is that Uranus has always been more active than we thought, and Voyager's instruments simply couldn't see the signal at the level Webb can. Either explanation is uncomfortable, because either explanation means the classification we've been using was built on a measurement we didn't have the sensitivity to trust. And here's the harder question. If we misread the internal state of a planet in our own solar system, using a probe that flew past it at close range, what confidence should we have in any measurement of a planet we've never visited at all? Every ice giant model calibrates against Uranus and Neptune. Neptune has never been visited by an orbiter either. two flybys decades ago are the empirical foundation for our entire understanding of ice giants. We didn't study Uranus, we glanced at it. Then we built textbooks around the glance. That's not a rhetorical flourish, it's the literal history of our knowledge. Voyager 2's encounter with Uranus in January 1986 lasted about 6 hours of close approach. 6 hours. Every diagram of Uranus's interior, every calculation of its magnetic field geometry, every model of its rings, every extrapolation to similar-sized exoplanets has been built from data collected during those 6 hours. No orbiter has ever gone back. No lander, no atmospheric probe, nothing. Now put that against the other planets. Mars has been continuously observed by orbiters since the 1970s, with multiple active rovers on the surface today. Jupiter had Galileo from 1995 to 2003, and now has Juno. Saturn had Cassini for 13 years. We watched Saturn's seasons change. We landed a probe on Titan. Pluto has more high-resolution surface data than Uranus, because New Horizons flew past it in 2015 with better instruments than Voyager carried. A dwarf planet on the edge of the solar system is better characterized than the seventh planet from the Sun. Let that sit for a second. And here's the part that makes the crack worse. The Voyager 2 flyby happened during Uranian southern summer, when the pole was pointed directly at the Sun. That's an atmospherically abnormal season. Uranus's extreme tilt means 20-year stretches where one pole roasts and the other freezes in darkness, and the flyby caught it at the peak of that skew. We built our understanding of normal Uranus from a snapshot taken during its least normal moment. Which means the model isn't just built on limited data, it's built on limited data collected at a bad time. This is what fragile science looks like. Not fake science, not bad science, fragile science. Science that was the best anyone could do with what they had, that got treated with more confidence than the evidence supported, and that is now being tested by an instrument sensitive enough to reveal how thin the foundation actually is. Webb is not disproving planetary science. Webb is showing us where planetary science was extrapolating past its data. And that pattern is not unique to Uranus. Neptune has one flyby. Triton has one flyby. The entire Kuiper belt has been sampled by one spacecraft visit, ever. Our confident-sounding descriptions of the outer solar system rest on a handful of brief encounters, most of them decades old. So the honest reading of Webb's Uranus data is not that we found something surprising. It's that we found evidence our model was under-tested, and we don't have a way to test it further without doing something enormous. The instinct is reasonable. If Webb has raised a serious question about Uranus, send a spacecraft. Observation reveals a mystery. Mission answers the mystery. But the gap between we should return to Uranus and we can return to Uranus is not a linear step up in difficulty. It's a categorical break. Start with the trajectory. Voyager 2 reached Uranus in 9 years, and it only did that because of a rare planetary alignment called the Grand Tour, which lined up Jupiter, Saturn, Uranus, and Neptune in a geometry that only occurs once every 175 years or so. That alignment gave Voyager the gravity assists it needed. That geometry will not repeat in this century in a form we could use. Without a comparable alignment, a dedicated Uranus orbiter would need to rely on a Jupiter gravity assist, which requires launching during a narrow window in the early 2030s. The 2023 Planetary Science Decadal Survey, published by the US National Academies, named a Uranus orbiter and probe as the top priority flagship mission for the next decade, specifically because of that window. Miss it, and the next viable trajectory pushes arrival into the 2040s or later. A slipped launch doesn't cost you months, it costs you a decade. And that's before you build the spacecraft. Uranus is about 19 astronomical units from the Sun. Sunlight there is roughly 1/400th of what a spacecraft receives at Earth. Solar panels are effectively useless. You need a nuclear power source, which means plutonium-238. The US supply of plutonium-238 was allowed to run down for decades and only recently restarted domestic production. Stockpiles are limited. Every mission that needs it draws from the same constrained pool. Then communication. The round-trip radio signal to Uranus is roughly 5 hours and 20 minutes. That means every command arrives more than 2.5 hours after transmission, and any response takes another 2.5 hours to come back. There is no real-time operation of a Uranus spacecraft. By the time you know something went wrong, it's been wrong for hours. Then thermal management, in an environment approaching absolute zero. Then mission lifetime, because the whole system has to survive a multi-decade journey followed by years of active operation. Then budget survivability, because a mission that takes 20 years from approval to first data has to outlive multiple administrations. Every axis multiplies. This is what scale rupture looks like. A Uranus mission is not a bigger Mars mission. It is a fundamentally different class of engineering problem. The window is narrow, the cost is enormous. If it closes without a mission committed, the next honest look at Uranus happens after most people watching this are gone. The Kepler Space Telescope launched in 2009. TESS launched in 2018. Together with Webb and ground-based follow-ups, they have detected thousands of exoplanets. And the single most common type of planet found around other stars is not Earth-sized. It's not Jupiter-sized. It's a category we call sub-Neptunes, planets between Earth and Neptune in size. Small ice giants. That's the most common planet type in the galaxy, and we have exactly 2 examples of it in our own solar system. Uranus and Neptune, and we've barely visited either. Which means every conclusion astronomers draw about sub-Neptunes, every estimate of their atmospheres, every calculation of whether they could host liquid water at any depth, every assessment of their potential habitability is extrapolated from what we think we know about Uranus and Neptune. And what we think we know about Uranus, Webb just told us, is wrong in ways we haven't fully mapped yet. Now think about what that means. When you read a headline that says, astronomers find potentially habitable world 40 light-years away, that assessment is built on models. Those models require assumptions about the interior structure, the heat budget, the atmospheric behavior of ice giant-scale planets. Those assumptions come from Uranus and Neptune. Those assumptions are, as of now, on shakier ground than the headlines suggest. The confidence in those announcements is borrowed confidence, and the loan just came due. Imagine trying to build a global weather forecasting system by studying one storm once in 1986 for 6 hours during that storm's most unusual season. Then imagine using that forecasting system to predict storms on every continent for the next several decades. You would produce predictions. They would sound authoritative, and you would have very little basis for trusting any of them. That is roughly where we are with sub-Neptune exoplanets. Not because scientists are careless, Because the physical constraints of studying outer planets are punishing, and the field has had to work with what it has. But the work with what you have era is ending, because Webb is now producing data sharp enough to expose where the assumptions were thin. Every time you've seen a news story in the last decade announcing a promising exoplanet, or estimating how many potentially habitable worlds exist in the Milky Way, the underlying confidence in those numbers depends on our ice giant models being roughly correct. If those models are wrong, the entire cascade of conclusions gets weaker. This is not a story about Uranus being interesting. This is a story about Uranus being the calibration point for our understanding of most of the planets in the galaxy, and the calibration point being unreliable. Which brings us to the part of this story that is not about physics at all. It's about money, timelines, and institutional inertia. The 2023 Planetary Science Decadal Survey is the closest thing planetary science has to a consensus roadmap. It is written by the community, reviewed by the community, and it sets priority order for what missions NASA should attempt over the following decade. In the 2023 survey, the top priority flagship recommendation was a Uranus orbiter and probe. The estimated cost is roughly $4.2 billion. The estimated development to arrival timeline is more than 20 years. Neither number is unusual for a flagship mission to the outer solar system. Both exceed anything NASA's current planetary science budget line can absorb without displacement. Because NASA's flagship budget is already fully committed, Mars sample return has experienced significant cost overruns and schedule delays. Europa Clipper, launched in October 2024, is now in cruise phase and will require operational funding for years. Artemis, the return to the Moon program, is consuming a substantial portion of NASA's human spaceflight budget. There is no unclaimed line in the budget waiting for a Uranus mission. So here's the paradox. Webb's discovery increases the scientific urgency. The Decadal Survey named it the top priority before Webb's most recent data made the case even stronger. But the funding system that would have to translate that urgency into an actual spacecraft does not respond to scientific urgency. It responds to political will, budget cycles, and the presence of an unoccupied slot in the mission queue. There is no unoccupied slot. Compare this to Cassini-Huygens. Cassini was first proposed in the 1980s, launched in 1997, arrived at Saturn in 2004, operated until 2017. That timeline, from initial proposal to end of mission, was almost 35 years, and it happened with strong political and international backing. NASA and ESA partnered on it. Congress supported it across administrations. It survived multiple near cancellations, and it still took that long. A Uranus orbiter, starting from where we are today, is competing against missions that already have that kind of momentum. It has to build political will from scratch, secure the plutonium-238 supply, meet the early 2030s launch window, and sustain funding through multiple administrations. Here's the human consequence. The scientists who will design a Uranus mission are being trained right now. They're graduate students today. Some will retire before the mission launches. The scientists who received the first orbital data from Uranus may not have been born when Voyager 2 flew past in 1986. A single Uranus mission will span generations of scientific personnel. We know how to build it. The problem is that the institutional apparatus that would build it is not currently configured to build it, and reconfiguring the apparatus takes time we may not have in this launch window. NASA, ESA, and space science communicators broadly have institutional reasons to frame Webb's Uranus findings as wonder rather than warning. Those reasons are not conspiratorial, they are structural, and understanding them is important, because otherwise the softening looks dishonest when it's actually predictable. Public funding for space science depends on public excitement, not public alarm. The image that goes viral, the caption that gets shared, All of it has to feed the machine that generates political support for the agency's budget. Stunning new image of Uranus feeds that machine. The foundational model of ice giants may need to be rewritten, does not. It might even damage the machine because it invites congressional questions about why NASA didn't know this earlier, why the follow-up mission isn't already in development, and whether the agency's current priorities are correctly ordered. Career scientists know this. Saying we were wrong for 40 years in public does not invite budget increases. It invites budget scrutiny. And scrutiny in the current fiscal environment is dangerous, because any admission of error can be weaponized. The safer move is to frame the discovery as a triumph of the instrument, which redirects attention toward Webb's success and away from the gap in the underlying science. International partners share missions. When ESA and NASA collaborate, disagreements about interpretation get smoothed for the sake of coordination. Nobody wants to be the partner who broke the messaging discipline. So the joint statements stay measured, and the internal debates about what the data actually means happen in specialist journals and private conferences, well below the threshold of public attention. This is not a claim that anyone is lying. It's a claim that institutional communication is optimized for continuity, not disruption. And when the underlying data is disruptive, the messaging lags the science, sometimes by years. What's being underplayed, specifically, is the degree to which Uranus-based assumptions propagate into exoplanet habitability estimates, the narrowness of the launch window for a follow-up mission, and the fact that the scientific community privately treats this as urgent, while the public framing treats it as delightful. The image is real. The wonder is real. The gap between what scientists know and what the public is told, that's real too. None of this means the agencies are behaving badly. It means the incentive structure they operate inside produces a specific kind of communication. And that communication systematically prioritizes reassurance over accuracy when the two conflict. If you want the sharper picture, you have to look past the official framing and into the working papers and the decadal surveys. That's where the honest tone lives. Here's the widest frame. Webb's Uranus image is not primarily about one planet. It's evidence that our confidence in settled planetary science is systematically overstated, and that the tools we now have to observe are outrunning the tools we have to explore. Think about what Webb can do. It can resolve atmospheric features on planets in our own solar system that ground-based telescopes couldn't touch. It can detect chemical signatures in exoplanet atmospheres light years away. Every month, it produces observations that raise legitimate scientific questions. And those questions accumulate faster than mission architecture can respond to them. If Uranus, a planet in our own solar system, can hide an active interior from us for 40 years, then our confidence in every unvisited world is proportionally weaker than we admit. Neptune has been visited once. Triton, its largest moon, which shows evidence of possible subsurface activity, has been visited once. The Kuiper Belt objects have been visited once by New Horizons. And only Pluto and Arrokoth got close-up looks. Everything else is inferred. And Webb keeps producing anomalies. Its observations of Titan have raised new questions about atmospheric methane cycles. Its exoplanet spectra have revealed chemical signatures that don't fit current formation models. Its deep field images have shown galaxies at redshifts that challenge assumptions about the early universe. Every one is a legitimate discovery. Everyone, in an era when we could mount responsive missions, would demand a follow-up. Most, in our era, will not get one. We are entering a period where observation dramatically outpaces exploration. We can see mysteries we cannot reach. That is a new condition for astronomy, and it's uncomfortable, because science depends on the ability to test hypotheses. And if the only test available is another mission that will take 20 years and $4 billion, then most of the hypotheses will remain untested for a generation. For the first time in modern astronomy, our best instruments are producing more legitimate questions than our best missions can answer within a human lifetime. Compare this to earlier eras. In 1610, Galileo pointed a telescope at Jupiter and discovered its 4 largest moons. That observation broke the geocentric model. It took nearly 400 years for a spacecraft to arrive at Jupiter and study those moons in detail. Civilization then had the patience, or the slowness, to wait. We are now in a Webb-era version of that same gap. Our instruments are showing us things faster than our missions can catch up, and we don't have 400 years of civilizational patience the way earlier eras did. We have decades, maybe. Here is the verdict. Uranus is measurably warmer inside than dead ice giant physics allows. The rings, atmosphere, and thermal profile don't match 40 years of modeling built on a single 1986 flyby taken during the planet's most atmospherically abnormal season. Every follow-up option requires launch windows, funding, and political continuity that are not currently secured. The exoplanet science that shapes humanity's picture of habitable worlds elsewhere is standing on the same shaken foundation. And the institutional messaging is systematically softer than the underlying data warrants, not because anyone is lying, but because the incentive structures reward reassurance over accuracy. That is the case. Every piece of it is real. Every piece of it is supported by published measurements, official mission documents, or the public record of NASA's budget and priorities. The comfortable interpretation of Webb's Uranus image is that it showed us something beautiful. The honest interpretation is that it showed us how much we had assumed and how little we had verified. Both interpretations use the same photograph. Only one of them looks at the caption underneath the caption. Let me be clear about what I'm not saying, because the misreading matters. I am not saying space science should stop. I am not saying that NASA or ESA scientists have failed. I am not saying that Webb was a mistake, or that the mission concepts on the table are unworthy. I am saying the opposite. Webb is doing exactly what it was built to do. It's finding the places where our assumptions were thinner than our confidence. That is what a great instrument does. The problem is not the instrument. The problem is what comes after the instrument. The mission architecture to answer the questions Webb has raised still exists on paper. The launch window for a Uranus orbiter is still, barely, open in the early 2030s. The scientists who could design and build the answer are alive right now, working today, some of them watching this. Whether we act inside the window is not a scientific question. The scientific case is made. It's a civilizational question. It's a question about what a society chooses to fund, what it chooses to prioritize, and what it's willing to wait for. That first sharp Webb picture of Uranus, with its rings glowing in infrared, the one that got called stunning across every news outlet, read carefully, is a warning. A quiet one, delivered in the polite language of science, but a warning. Webb didn't just show us Uranus, it showed us the size of what we chose not to look at. And it's asking, without saying it out loud, whether we're going to keep choosing that.